Transformers changed sequence modeling and enabled this huge technical breakthrough with chatbots and agents taking over the world. But what if self-attention was not the end of the story? What if there was another model that could match transformer-level performance while scaling better to very long sequences? If you haven't been following sequence modeling research very closely over the last couple of years, there's a good chance that you've never heard about Mamba. So let me give you a quick recap. Mamba is built on state space models, or SSM, a line of research that traces back to recurrent neural network reimagined through ideas from control theory and continuous time dynamical systems. It achieves performance comparable to transformers on several benchmarks, and in some cases, especially those involving very long sequences, it can even outperform them. In which situation would we use Mamba instead of transformers? They are very explainable, they come with an incredible ecosystem of tooling, they've driven some of the biggest breakthrough in modern NLP. So why even bother looking at an alternative? I've been working with Mamba for several months now, and I've developed a clear intuition for where Mamba really shines and why it's worth understanding. My name is Mathieu and you're watching ML Instinct. Welcome to this first video in a series on the Mamba model. Please note that this is going to be easier to follow if you already have a rough idea of what transformers and recurrent neural networks are, in particular the attention layer, I would say. If this is not the case, I suggest you go and check those first. Now, let's dive in. In this first part, we'll step back and look at the different ways sequence models are actually used in practice. We'll cover 3 common settings, and we'll then pick one of the settings as our reference use case. Based on this use case, we will then compare how recurrent neural networks, transformers, and Mamba approach the problem and what trade-offs they make. Finally, we'll move to a more technical deep dive into one of Mamba's key ideas, how it enables parallel processing despite being rooted deeply in state-space dynamics. This last part is more mathematical and implementation oriented, and this is where we'll unpack the parallel algorithm that makes Mamba so practical at scale. So when you're doing sequence modeling, whether in NLP or in other domains, there are actually several different ways you can use your model, depending on what you're trying to compute. A very common use case, especially recently, is autoregressive decoding. So you start from an initial context, such as a prompt or a few tokens, and you predict the next token, and the next, and so on. Each prediction depends on the previous one, so generation is inherently sequential and interactive. This is the standard setting for language generation, chat models, and text completion in general. A second use case is quite different. You could have the entire input sequence available upfront, and the goal is to produce an output on every position. This could be token level likelihoods, anomaly scores, or any other per token signal. In a third use case, the full sequence is still processed, but only a single output is required. So this might be a classification label, a summary representation, or some global state that aggregates information across the sequence. To me, the second setting is arguably the most fundamental one. It is exactly the setting used during training. We feed the model a complete sequence and ask to produce outputs at every position, optimizing typically the parameters, but by maximizing likelihood. In my own work with Mamba, particularly for anomaly detection, this is also the primary inference setting. But this is also where parallelism matters most, right? Because the full sequence is known in advance, the model's ability to process tokens in parallel has a major impact on efficiency and scalability. So for the rest of this presentation, we will focus on the second use case and take the training setting as given. This will let us clearly see what Mamba does differently and why its parallel algorithm is central to the story. Let's move on to the comparison. Comparing in an exhaustive manner the 3 models would require to go through their whole architecture, which would frankly take us several hours. So I will quickly present the high-level view of Mamba architecture, taking for granted that you have a rough idea of transformer and RNN high-level architecture. A Mamba model is basically composed of residual blocks stacked on top of each other. Each of them features a Mamba block preceded by a RMS norm and wrapped inside a skip connection. Each Mamba block features projections, a convolution, a nonlinearity with a gating mechanism, and the SSM block. The SSM block is the one maintaining a state and ensuring that context is passed from some past tokens to current computation. Now that the heart of Mamba, the SSM block, is identified, we can compare its formula to the hearts of transformers and RNNs. Here I will write what I consider to be the core computation for each of these three model families, focusing only on how they process context. So let's start with the transformer, since it's the most familiar to most people. For a given position t, the output yt is computed as a weighted sum over all previous values vectors, vi, from I equals 1 to up to t. The weights come from applying a softmax to the dot product between the query qt and all the keys key from 1 to t, scaled by the model dimension. The important thing to notice here is that context is incorporated through an explicit interaction with all previous tokens. For a single yt, the computation involves every token in the prefix. There is no persistent state. Context is recomputed from scratch at each layer using these large attention matrices. Now let's move to the recurrent neural networks. The picture changes. Here, context is summarized in a hidden state, ht. The new state, ht, is computed by applying a nonlinearity to a linear combination of the current input, xt, and the previous state, ht-1, using rate matrices wx and wh. The output, yt, is then obtained by applying a linear projection, wo, to the state, ht. In this case, all past context is compressed into ht-1. And this compression is updated sequentially. Because of the nonlinearity in the state update, the computation is inherently sequential. You cannot compute ht without first computing ht-1. Finally, we have Mamba, expressed through its state space model formulation. At first glance, this looks really similar to a recurrent neural network, right? We still have a state ht, and it still depends on the previous state ht-1, as well as the current input xt. But there are two crucial differences. First, the state update is fully linear. The new state is computed as a linear combination of the previous state and the input, using matrices A and B that depend on a quantity delta t. There is no nonlinearity inside the state transition itself. Second, the matrices A and B actually depend on delta t, which itself is a function of the input. This means that the update remains linear, but it is input dependent, allowing the model to adapt how it propagates information through time. The output yt is then obtained by applying a linear projection c to the state ht. So just like recurrent neural network, Mamba stores context in a recurrent state. But unlike recurrent neural networks, the state evolves linearly. And unlike transformers, context is not recomputed through pairwise interactions between tokens, but carried forward through its state space dynamics. This linear structure is not a minor detail. It is the key property that will later allow us to reformulate this recurrence and compute the states in parallel over the whole sequence. Even though Mamba looks recurrent, the mathematics behind this update is what makes its parallel processing possible. Now let's look at the computational complexity of these models to formalize how recurrent neural networks, transformers, and Mamba scale in practice when we run a forward pass on a given input sequence. On this slide, I'm using three main variables. T is the sequence or prompt length, D is the hidden size, and L is the number of layers. We can immediately set L aside because this factor behaves the same way for all three models. If you stack more layers, the computation scales linearly with L, whether you're using transformers, RNNs, or Mamba. What is much more interesting is how the cost scales with the sequence length t. Starting with transformers, the time complexity scales quadratically with t. This comes directly from the self-attention mechanism. So you build queries and keys of size t by d, and then you multiply q by the transpose of key, and you get this t by t matrix. This operation alone costs on the order of t squared times d. You also need to store this t by t attention matrix in memory before applying the softmax, which means the activation memory also scales quadratically with t. There are many optimizations and variants like linear attention, but the standard transformer architecture behaves this way. The upside is that this computation is highly parallelizable because it is essentially large matrix multiplication that map very well to GPUs. If we now look at recurrent neural networks, the scaling story is very different. In an RNN, processing a new token takes constant time with respect to the sequence length. So the total cost scales linearly with t. However, the hidden-to-hidden matrix is a full matrix of size d by d, which means that each step costs on the order of d squared operation. This explains why the time complexity scale as t times d squared. Memory also scales linearly with t, since we typically need to store activations for backpropagation. The major downside is that there is no parallelism over time. Each step depends on the previous one, so the computation is strictly sequential. Mamba sits in between those two worlds, and in some sense combines their advantages. Like RNNs, its forward pass scales linearly with a sequence length t, so it avoids the quadratic blowup of transformers. But unlike RNNs, the state's transition matrix in the SSM is diagonal most of the time. This drastically simplifies the state update and removes the d squared cost. As a result, the time complexity scales at t times d, just like the memory cost. And crucially, despite being defined as a recurrence, Mamba allows full parallelism over time. As we'll see in the next section, this comes from a specific algorithm known as a prefix scan, which lets us compute all states in parallel. In terms of performance, this table summarizes the general trends observed in long-range benchmarks such as LRA. Transformers tend to perform very well on short and medium-length sequences, but the time and memory costs grow quickly as t become large. Recurrent neural networks generally struggle on this benchmark due to vanishing gradients and limited long-range accuracy. Mamba and other SSM-based models tend to perform strongly on long sequences, often outperforming RNNs and sometimes transformers when t is large, although they can be slightly worse than transformers on very short sequences. So the key takeaway from this is that Mamba achieves linear scaling in both time and memory like RNNs, while retaining full parallelism like transformers. We have just looked at empirical and experimental results, but the authors of Mamba also make a strong theoretical claim in their paper, Transformers are SSMs. The core idea is that under certain constraints, structured state-space models can be as expressive as self-attention. The key observation in the paper is that the dual or quadratic form of a structured state-space model can be written in a way that looks very similar to self-attention. In this formulation, the output is still obtained from a query key value like computation, but instead of applying softmax to the query key product, the softmax is dropped and the resulting matrix is multiplied element-wise by an additional mask matrix L. The coefficients of this mask are input-dependent and bounded. Under these assumptions, this dual SSM computation is mathematically very close to an attention layer. This is what allows the authors to argue that in terms of expressivity, anything a self-attention layer can represent can also be represented by a model like Mamba, at least within the scope of these constraints. Let's now move on to the central part of the presentation, how Mamba processes an input sequence in parallel. This relies on the prefix scan, also known as the Blelloch scan, introduced by Guy Blelloch in the 90s. When I first encountered the Blelloch Scan, I noticed that clear and accessible explanations were surprisingly hard to find. It's often confused with the Healy-Steele scan, which is simpler but also more limited. And in deep learning contexts, it's usually illustrated through cumulative sums. While that example is useful, it can be restrictive and doesn't always make the underlying idea clearer. Many explanations also rely on tree-based views, admittedly easier to grasp, even though in practice, the scan is commonly implemented as an in-place operation on a vector. All of this motivated me to give my own explanation in this video, using string concatenation as the running example. String concatenation is more general and has exactly the properties needed to enable the prefix scan. Once this example is clear, I'll show formally why the SSM computation in Mamba behaves in the same way as string concatenation. This will ultimately justify why the prefix scan can be used to parallelize the SSM operation. Here, the goal is to concatenate 8 letters in a cumulative way. We start from the 8 individual letters on the word machines, and we want to obtain a vector that contains the cumulative concatenations of these letters. A naive approach would be to concatenate them one by one, right? First M with A, then MA with C, then MAC with H, and so on. The number of steps required to compute the final result is linear in the sequence length, and this is where the prefix scan comes into play. The prefix scan uses a divide and conquer strategy to reduce the number of steps to one that scales logarithmically with the sequence length. It does so through 2 phases, an upward pass and a downward pass. Let's start with the upward pass. We begin with a vector of single letters. In the first step, adjacent letters are concatenated together. In the next step, those resulting pairs are grouped and concatenated again. And this process continues until the full word is obtained. You can already see where the logarithm comes from. At each step, the longest string roughly doubles in length. It's important to note that the total number of concatenations is actually the same as in the naive recurrent approach. What changes is the number of steps, which is reduced thanks to parallelization. Here we understand where the divide and conquer comes from. For example, Mush and Eins are processed independently and in parallel before being concatenated together to form machines. At this point, we do obtain the final result. However, we cannot stop here. As you can see, the intermediate cumulative concatenations are not all correct yet. This is where the downward pass comes into play. The downward pass starts from the top of the computation produced by the upward pass. First, we remove the final result from the structure and store it separately, replacing it with the empty string. Then we perform concatenations at the same position as in the upward pass, but in reverse order. For instance, the empty string is concatenated with mush, and the empty string replaces mush in the vector. Then the empty string is concatenated with an MA and replaces it, while MACH is concatenated with in and replaces it. In the diagrams, straight arrows represent concatenations and dots indicate replacements. As you can see, this process reconstructs the full set of cumulative concatenations step by step. Just like the upward pass, it runs in a number of steps that scales logarithmically with the sequence length. And it performs exactly n-1 concatenations. Overall, the upward and downward passes together requires twice as many concatenations as the naive approach. The benefit is not fewer computations, but fewer sequential steps, roughly 2 times logarithm of n. The downward pass is admittedly a bit trickier to grasp, so feel free to pause the video and go through it carefully. My intuition is the following. The upward pass computes the correct values at indices that are powers of 2. This acts as prefixes. The downward pass then propagates these prefixes to fill in the values in between. For example, at the beginning of the downward pass, mash at index 4, so 2 power of 2, is correct. And machines at index 8, 2 power 3, is also correct. Between them lies the suffix in, which can straight be concatenated to mash to form machine. Then the suffix I is concatenated next, while E gets concatenated to mash, and this reconstructs all cumulative concatenations from mush to machines. Finally, the way the algorithm is structured introduces a one-element offset in the final vector, but the core idea should now be clear. Now that we've seen how the prefix scan works with string concatenation, let's show that the SSM formulation has the same essential properties as string concatenation. At a high level, an SSM processes an input sequence in a recurrent way. Starting from an initial output x0 and an empty context, it produces a stage h0, which in turn generates an output y0. Then h0 is combined with the next output x1 to produce h1, which in turn produces y1, and so on. This is the standard recurrent network setting. I introduced the SSM formula earlier, so let's take a closer look at it. Recall the use case. We have access to the entire input sequence at once, so all the xi values are known. The matrices B and A have already been computed from the input, and our goal is to compute the states ht for all positions. To simplify the notation, we can perform a change of variables. In practice, most Mamba implementation absorb the effect of delta t and b into x and delta t into the matrix A. This leads to the very simple recurrence formula with ht equals to xt plus at multiply matrix multiplication by ht minus 1. So let's define a new function big H. It takes as input a sequence of indices and outputs a vector. These indices comes from a fixed index set. And we define big H as follows: H of an empty sequence equals null vector, and H of a single index element equals xi, the vector xi. And for any sequence I1 to In, H is defined recurrently with H of the whole sequence equals H of the last index plus A of the last index multiplied by H of the whole sequence but the last index. Every sequence is either empty or can be built by appending a new index to an existing one. The result of this is that these rules that I defined earlier uniquely define H on all sequences of indices. If you're paying close attention, you may already notice that H0 to T follows exactly the SSM recurrence. Writing this out gives back HT as defined above. In other words, we've defined a function H on a large domain, all sequences of indices, but whose behavior on the specific sequence 0 to t, so 0, 0, 1, 0, 1, 2, and so on until 0 to t, matches the original SSM state space computation formula. In the same way, we can define a function big A on a sequence of indices that would return the identity matrix for the empty sequence, and for a non-empty sequence would return the product of the corresponding AI matrices. From this definition, it is straightforward to prove by induction that H satisfies the following property. For any two sequences of indices U and V, computing H on their concatenation can be done in a single operation using HV, AV, and HU. For A, this property follows immediately from the definition without even needing induction. As a brief mathematical aside, defining this operation together with the empty sequence as a neutral element gives us a monoid structure. That's a nice observation, but not essential for our understanding here. What really matters is this. Our goal is to compute H0, H01, H01 to T in parallel. Does it sound familiar? I bet. Earlier, we showed how to compute cumulative string concatenations in parallel using a prefix scan. And we've now shown that in a single operation, we can compute HA for the concatenation of two sequences of indices. This means that we can repeat exactly the same procedure as with string concatenation, replacing the string concatenation with the computation of HA for the new sequences of indices. And that's the key result. And now the prefix scan can be used to parallelize the SSM state computation. Instead of a number of steps that scale linearly with the sequence length, we now only need a logarithmic number of steps. This may sound like nothing, but in practice it's a huge win. It can reduce training time on long sequences from hours to a few minutes. The same idea also applies to inference if it is performed chunk by chunk. To wrap things up, today I walked you through some of the key ideas that make the Mamba model stand out. We compared it to recurrent neural network as well as transformer in terms of complexity, scaling behavior, and expressivity. Then, in the more technical part, I showed you how the SSM formulation can be efficiently computed over long sequences using the Blelloch parallel scan. This was my very first video, so I really hope you enjoyed it. If you have any feedback, questions, or suggestions, feel free to drop them in the comments below. I read them carefully. Thanks for watching and see you in the next one.